follow-up discussion on design of experiment using Excel, as well as we are going to compare the result in many tabs. And the method we are going to use it is Plackett-Burman screening method. And to do that, so we need to know few things. There are 10 points we have jotted. Those will be useful to know. First, set the acceptance criteria. Throughout the statistics, same rule is there. For example, generally we say confidence is 95 percentage confidence, right? That means the risk you will be living with is alpha, that is risk. You will be living 5 percentage, right? Let's assume that you need pretty much very, very high 99 percentage. That means the risk is 1%, and so on. Like, if it is 90 percentage, the risk you will be living with 10 percentage, right? So in design of experiment, you can vary based on your requirement, but the default value generally we use it is alpha 5 percentage, 95 percentage is the confidence interval, right? And the second thing is select the factors, what factors you need. In this case, we're going to take a look on factor A all the way to G, like 8 factors we're going to learn, right? And then define the levels, like low, usually it is like binary, like low, high, low or high, on or off, 0, 1, -1, +1, or 0 or 1, and something like that. Define the levels. So as I mentioned in the previous video, even you have any variable data, let's say variable data with speed, and you have a speed like, for example, let's say train speed, we say 90 kilometer per hour, 100 kilometer per hour, and then you have 110, 70, and all that, right? All that you will convert into binary form, right? In the binary form, how you will convert? For example, let's say you will say low or high, example, right? So anything below 60, you may say low. Anything above 60 or greater than 100, you may say high, example, right? So like this, you need to convert. The same thing here also it has been done. So sample run is very, very important. The simple formula for the run is that, as we recalled in the previous one, L the power of F, right? L is level. Let's say in the previous, now we learn level, let's say 2, binary, and 8, right? So that means 2 the power of 8. So in practically, sometime it is not possible to do that, right? We are gonna learn that also as well. For example, theoretically, we need 256 runs, right? We have 8 factors, but generally speaking, let's say if you have only 3 factor, then 8 is good enough. But using 8 itself, we can do 8, the 8 factors, right? That we are going to discuss as we go along. And then next one is that randomization is a key. Whether you talked about measurement system analysis, whether you talked about hypothesis, whether you talk any statistical ground rule, is that you need to randomize the order, right? So exactly the same rule apply to design of experiment. Run and record. So every time you run that one and record the value, keep track of it, keep tap of it, right? And then, so this is a significant factor, right? So p value. So using the ANOVA, for example, the interaction it will give in ANOVA, analyze of variance, and keep a tab on that ANOVA factor. For example, p value, right, is less than or equal to alpha value. That means it is significant, right? P value probability are significant, right? Let's say if we have p value, we are getting is 3%, and we can go ahead, the as per the risk is 5%. This is lower than this, so that means it is significant. The same thing, let's say I'm just keeping that factor as same 5% alpha risk, and let's say I'm getting a 33%, that means it is not significant, right? So the same rule, hypothesis rule, apply to this also as well. So in design of experiment, and one of the things which we'll be using it is that hypothesis testing and visualize the result. It is not, in the previous video I talked about how to see the interaction, right? Particularly this interaction will play a super major role, like how to see whether it is interacted or not interacted, you will see. And for example, in the previous video, just to recap a bit, this is, we call it as no interaction, and this one is because 0, and this is interaction 1, somewhat interaction. And you can see this is the 10 value we are getting in the example. And then this is interaction 2, that is moderate interaction. And the interaction number 3 is that, see, this is super duper good, right? So interaction 3, that you get the point of intersection and all that, and then theoretically, even if you do that mathematically, you get that value, right? So this is same apply here also as well, right? So visualize the result and all that, and then confirm the finding. Let's say some factors are interacting. You do it to ensure that those are confirmed. So you always have to refine your findings, refine whatever the method and everything you're doing it. You please try to refine your factors and reduce the number of factors, and anything noise factor, try to take it out and keep doing it, right? Reduce that as much as possible. So this is we set the stage. Now let's go ahead and take a look on Plackett-Burman method. So this is the data it has given. You see that there are these are the factors, right? So you see 8 factors are there. For example, A is nothing but pulse, intervals, C is current, D is arc level, R suppress, short delay, and servo feed and serve. I mean 8 factors we have. How many levels we have? We have only 2 levels. For example, minus 1 denotes it's a low, and plus 1 denotes is a high, right? You remember that whatever the variable, all these are variable. Whatever the variables you have, like continuous data, you need to convert into the discrete data, that too in binary form, so that you can do the analysis. So, for example, run number 1, there are 8 runs being done. Let's say this has to be randomized. Let's say you can do the randomization. So this is all, for example, factor 1, pulse has been kept low, and interval has been kept low, and all these are kept low for current, arc level, R suppress, short delay, serve feed, and so. And then let me take one, for example, this one, 8 condition, right? 4 factor, that is pulse, interval, current, and arc level has been kept high, and the other factors been kept low, like R suppress, short delay, serve, feed, and serve been kept low, right? So like this, you get the value. So this is the value. For example, they have just find out what is the value of resistance we are getting it if we keep this factor, and then we can replicate this also. So these are all number of replications, right? So how much values you are getting it? You are getting it the total interaction 48, right? And 8. So 8 has been done 6 times is been done, right? So number of runs is 8, and it has this is runs, and then this has been replicated in 6 times. So this is a replicate, meaning repeated. For example, you set the reading and take it down. First time it gives 0.06, next time 0.1, 0.07, and this is called replicate. In other word, is called repeating, right? So the total n value you have is that 586 48, right? 48 value you have. So if you see here, right? So 48 counts you have. So, and then in the last video also we'll learn like how to find out the average. So average is quite straightforward, right? So you can take that average here, right? So anything like this is average. For example, let's say here the condition is being given, a count condition is given, but here let's say I'm just taking it like average of these factors. This is simple average value. You got 0.08, and pretty much the same value you get it. Let me delete this annotation. So you got this value, right? Almost the similar value. And then standard deviation. In the standard deviation, just like in the last video, we described that it has used standard deviation direct formula, right? So in the standard deviation, you have sample, you have a population, and then you have directly standard deviation, right? So standard deviation formula, you can directly use it, right? For example, the standard deviation of this 0.021, right? So this is the standard deviation one. So the same, this is using the standard deviation formula. And let's say you want standard deviation sample example. let's say standard deviation sample, and you take that one, the 0.01, and you are getting slightly, okay, maybe I will just keep it the same thing, same value. You can notice that the values are pretty much same, right? That means sample and standard deviation returns the same value. But if you look at the standard deviation, the population, you will get different value as such. Why you will get different value? So population will describe that, because in the formula, -1 gets applied, so therefore you naturally get different value. So this is slightly lower than this. But you see that slightly lower than this. So the one of the reason for this one is that the standard deviation formula n-1 gets applied here, right? So anyway, so this we got standard deviation, but either you use standard deviation formula like this, or you use standard deviation dot s. So this is done. Let me delete this. And then noise factor, signal to noise. So you know that it is a log of the log of standard, I mean average divided by standard deviation. For example, equal to log of average by standard deviation. And this is the same value we are getting it there also, right? And then drag this up. This log method gives you how much signal to noise ratio. And in the past video, we talked about more about how this has been, how it has been very useful. For example, we learned this one, signal to noise, right? Signal gives that how much, keep it here. So signal desired effect, and then it also tells us how much noise is there in the desired effect, right? So signal to noise ratio. Okay, so now these are all the factors. So once you update, for example, these are all the value being keyed. So only the value which is, for example, like pulse. This is what I was saying. The variable data has been converted into the discrete data in binary form, right? So let's say you have -5 is considered to be low, and pulse 11 considered to be high. Similarly, the same thing, right? So you can change this one. Wherever yellow is there, you can input your data and all that. And then factor 1, factor 2, all that two factor hits gets calculated. And then you have interaction matrix that also gets calculated. Furthermore, and you have a confounded also that gets calculated, and you see that this value is coming from, for example, S6, right? So this value gets calculated. Each factor, for example, S6, right? Each factor, this gets calculated as such, right? So then you have 8, and then the grant average, you get it this one, 0.12. And very importantly, we are talking about ANOVA. And ANOVA, few things we need to learn: degree of freedom, and sum of square alpha, the probability of test, mean sum of square F test, right? So you see that there are 8 factors, right? Out of 8 factors, only these factors seems to be significant. For example, this is one. I'm just going by the value. So 57 looks to be the very interacting one. And then let's say after that, the next number is 29. This is also a factor. That means serve feed will have an influence. And then the third one is that current will have an influence. And then let's say I'm just adding it to this whether to show whether the 80 percentage, and now it is just okay. So you see that this is playing role, right? Even 17 I'm taking it, and then to some extent 12 percentage arc level also playing role, right? So the data, I mean, normally distribution is very important, and if the data is known to be normal distribution, analyzing the within run data, design replicates yields higher confidence. You get because normal distribution, the data is normally distributed, you get the higher predictability, and this matrix does not conform to normality and all that, right? So because we have directly feed that minus and plus value, and we don't have a raw data of yield data or any variable data. Error in the result increase in the column greater amount of partial data. Example, if two replicates are taken for each run, then R1 R2 should be fully filled out. Okay. Now let's just take this data and let's take all this data and then I'm gonna put this. Maybe what I will do, I will just copy all of these data and put it in Minitab. Okay, so 7 and 8 we don't have. This is total average, right? I will go for total average itself. This is average. I will go for this value. And first thing what we need to do, as you know, that we wanted to confirm whether the same values are there or not. Go to start design of experiment, and then you have a factorial. First, define custom factorial. What are the factors? Our factors are A all the way to H. This we have selected. And then we have two level. You can see -1 +1 and all that, right? So up to H, we have the same condition. So this is okay. And then you can, I mean, if we already have that specify the order. For example, run order, we have run order. And then you can just specify that column order and all that we can do that. But I'm just skipping it now because it will give the data and then I will copy paste that. Give okay, give okay. So it has given the standard order, run order, blocks, and center point. Let's assume that this has been done in the same order. We can just tell that. So now define part is done. Where I have input this. What we have done is that we have done the design in design factorial and then custom factorial where we have given input. And then we need to analyze it. So output is only the C7, or you can take this average, but I will directly go for average. Output is also been inputted, right? You can see that just taking that value. So you see that the C, G, and A found to be important factor, right? Exactly the same we found here also as well. C, and you have G, right? And C, this is C, and then you have G, and then you have that A and all that is important factor. So let me go ahead and do that optimizations now. So DOE factorial, and then I have a lot of choices here. Let's say what I wanted to have. So for example, let's say I wanted to keep it response optimizer. Let's say I wanted to improvise or minimize the resistance. Example, I can do that. So this is the settings. It is recommending it, and for example, these three factor A, B, C should be kept low, and the remaining should be kept high. And this is shows that this is a parallel line, and this is no interacted, right? So this is highly interacted, and G is highly interacted. You get to know everything. And then similarly, you can also do, if you want bit more clarity, you can also do that the contour plot also as an example. Let's say you take two factors and you try to do that the factor, right? Or if you want, you have more choice because it is greater than three factor. You have more choices to do. For example, cube plot. Again, you can take any factors. So along with the confounded, it gives lots of information to you, right? And this is how we can do it. Similarly, Tagochi also you can do because Tagochi we can also use it. Let me quickly do that Tagochi also. Again, I need to do the same. Factor is A all the way to H is the factor, 8 factors. And okay, so this 8 factor has been inputted. I'm just checking whether the nice factor has been calculated. No. Okay. And then you can do the next one is analyze. Right? Same. Analyze is average. I'm just doing it. And it gives that analyze also. The last one is that we're going to take output, right? So here itself we can see We have got that output. Analyze. So you see, sorry. So you can see that all this equation, everything it has given, and whether significant, not significant, all that value it has given, right? So depend upon that one, we can just use it, right? So, but we have a lot of factors, so Plankett method will be more appropriate in this very case. I hope you find it useful. Please do like, share, subscribe. You have a wonderful day.